Hi, I'm Nick, and this presentation is for the second course in Duke University's AI Product Management specialization, Managing Machine Learning Projects. In this course, we've been learning how to identify opportunities for machine learning, apply key design decisions, and think through validation and risks. For my final project, I've chosen to tackle a problem in healthcare appointment booking. The problem is that patients often face frustration when their preferred provider is unavailable, which can lead to lost bookings and dissatisfaction. Currently, the fallback is for patients to check back later or book with another provider, but that doesn't fully address their needs. My solution is a machine learning-based system that predicts when slots might open for specific providers and dynamically offers wait lists for patients. Now, why is this an attractive opportunity for machine learning? Three reasons. One, we have strong data availability. Historical booking and cancellation patterns already exist. Two, ML can uncover provider-specific trends and cancellations that are too complex for simple heuristics. And three, this solution has a clear business impact: happy patients, fewer unfilled slots, and increased revenue. Now, before we move on, let's quickly cover the three key questions to ask when identifying a machine learning solution. One, is there really a problem? Two, can ML solve it? And three, does anyone care if we solve it? And in this case, the answer to all three questions is yes. Now, CRISP-DM is the framework we use for ML product development, guiding us through multiple stages, sometimes in a nonlinear fashion. I'll be focusing on just a few of the key elements relevant to this assignment, starting with business understanding. The target user for this solution is any patient using a healthcare marketplace who wants to book with a provider that lacks near-term availability. The problem matters because patients face frustration and may abandon the platform if they can't secure their preferred provider, which impacts both user satisfaction and business performance. Currently, the problem is partially addressed by suggesting other providers or encouraging users to check back later, but this solution is neither personalized nor efficient. To define success, we'd look at two key metrics: improving 7-day booking conversion rates and maximizing provider slot utilization. These directly tie to measurable outcomes like higher patient conversion rates and reducing unbooked time slots for providers. Additionally, relevant factors influencing the model include provider-specific data like cancellation rates and time slot fill trends, and external temporal variables such as holidays or seasonality, which can impact appointment behaviors. My solution starts with a unidimensional regression model that predicts the number of slots likely to open for a provider in the next N days. This forms a foundation for deciding if a waitlist should be offered and how deep it should go. To validate this, we'd follow an iterative approach. First, we'd start with UX research to test simple prototypes and understand user needs without using any real data. Then we'd use historical data to mock up scenarios and refine requirements. Next, we'd run simulations with real data using a heuristic in place of a model to establish baselines. Only then would we incorporate a simple ML model, evaluating and improving it through iterative testing. This approach ensures we're building a system that's user-centered and effective from the start. Okay, now for the fun part: machine learning system design. For this, I made three key decisions based on the trade-offs outlined in the course. First, Cloud ML versus Edge ML. I chose Cloud ML because latency isn't critical here, and we need centralized access to historical data for training and predictions anyway. Second, offline versus online learning. Offline learning here is ideal because cancellation trends evolve slowly, and batch retraining is cost-effective and robust. Third, batch versus online predictions. I went with batch predictions for efficiency, and because this enables easier monitoring of model drift. It also minimizes latency in the app UI. We could start by generating predictions relatively frequently, say every 15 minutes. With those design decisions in place, let's talk about potential risks in production. There are four primary risks and mitigation strategies. First, training serving skew. Differences between training and real-world data could lead to inaccurate predictions. We mitigate this by pre-processing input data consistently and regularly comparing training versus live data. Second, excessive latency. Slow predictions could frustrate patients. To mitigate, we'd optimize the model for fast inference and use low latency cloud infrastructure. Third, data drift. Provider behavior may change over time, so we'll monitor key metrics and retrain regularly. And finally, concept drift. The relationships between features and outcomes could evolve, requiring model updates every few months. To summarize, this product leverages machine learning to optimize healthcare waitlists by predicting availability and dynamically offering slots to patients. The system is designed to balance patient satisfaction, provider efficiency, and marketplace success while addressing key risks. If implemented, it could significantly improve the value of the booking platform to both patients and providers, and ultimately make it easier for patients to find the care they're looking for. Thanks for watching, and I hope this gave you some insight into how machine learning can address real-world challenges. Feel free to reach out if you'd like to learn more.